All right, so here in 1.7, we're going to be looking at how to find the inverse of a function if it exists. That's a question mark there. Not all functions have inverses. We'll find out, okay? So if we go to example 1, I have two linear functions, and we start off being asked to find some compositions. F of g of 5. Let's start there. That would be f of, we're going to plug 5 into g, so that would be 2 times 5 plus 1, which is going to be 11, right? So now we evaluate f at 11. That's going to be 11 minus 1 over 2, 10 over 2, or 5. And what I want you to notice is I started with a 5. That was my input, and my output is a 5. Okay, I get the same thing that I started with. G of f of negative 7, that would be g of negative 7 minus 1 over 2. Or g of negative 4, right? Which is going to be 2 times negative 4 plus 1, or negative 8. I'm sorry, negative 7. Negative 8 plus 1, so negative 7. Once again, my input was negative 7 on the original composition, and the output is negative 7. Okay. Now we want to find the overall compositions, f of g of x and g of f of x. So f of g, that would be f evaluated at 2x plus 1. That's 2x plus 1 minus 1 all over 2, right? Okay, these are, of course, going to cancel out. And then you have 2x over 2, which is going to reduce to just x. Once again, my input here is x, and the output is x. And then we go in the other direction, g of f of x, that's the same as g evaluated at x minus 1 over 2. So that would be 2 times that x minus 1 over 2 added with a 1. Those 2's are going to wipe out. And then the negative 1 and the 1 are going to wipe out, leaving me ultimately with just x. Okay, so anytime the two compositions in both directions equal out to x, that tells me that those two functions are in fact inverses of each other. You actually had a homework problem, if you recall, related to this. Okay? And this is really the only time composition is commutative, when you're working with inverses. Now recall, inverse notation, if the function is f of x, then the inverse notation would be represented by that. It looks like f to the negative first power, but you would say the inverse of f, or f inverse, right? Okay. All right, now go to example 2. We have those same two functions, and now we're asked to graph them. Okay. So I'm going to do f in blue here. Now, it would probably be helpful to think of that. What's going on with my pen here? That thought. All right, so that's equal to 1/2 x minus 1/2, right? When you see it like that, that's slope-intercept form. That can help you with graphing. Y-intercept is negative 1/2. And then the slope is 1/2, so I can rise 1, run 2 units. Keep on doing it. Or I could have gone down 1 and left 2. All right, so there is f of x. Now g of x is already in slope-intercept form. Let's pick a different color. I'll do red. 2x plus 1. Y-intercept is 1. And slope is 2, or 2 over 1, up to right 1. or down to left 1. Okay, and what we want to observe, we've already said that these two functions are inverses of each other on the previous page, right? Graphically, what we want to observe is we have a line of symmetry here. Okay, these two inverses are reflections across the line. This is y equals x. That is a property of inverse functions. Their graphs will always be a reflection over this line. Okay, some other properties that are listed down below. Properties 2 and 3. The domain of the original function is going to be the range of its inverse, and vice versa. The range of the original is the domain of the inverse. So you're just switching the x and the y values. Okay. Properties 4 and 5 were shown in the previous page. The composition of a function and its inverse in both directions will always equal x, right? Always equal x. Okay. All right, now we go to example 3, and here we're asked to graph the function, find its inverse, and graph that as well. Okay. So let's just graph f of x first here. It's a cube root function. Domain for this is all real numbers. You can take the cube root of any value, right? And let's do a table. Let's be strategic about this. I want to be able to take cube roots of perfect cubes, right? So think about some values of x that after I add 2 would create perfect cubes. Negative 10 would be a good option. Negative 10 plus 2 is negative 8. What's the cube root of negative 8? Negative 2. Good. So go ahead and plot that right there. Okay, I think negative 3 would be another good choice because negative 3 plus 2 is negative 1. The cube root of negative 1 is negative 1. Negative 2 would be a good choice. That's going to produce the cube root of 0 or 0. Negative 1 would also be a good choice. That'll give you the cube root of 1 or 1. And 6 would be one more good choice. Cube root of 6 plus 2 or cube root of 8 is 2. Okay, so we're going to label that f of x. All right, now to find the equation for this function's inverse, I'm going to switch the x and the y values in the equation and then solve it back for y, okay? So remember, f of x, that's the same as y, right? This is the original function. Okay, now I'm going to pick a different color here because what I'm about to create is now a new function. This is x equals the cube root of y plus 2. And I got to solve that back for y. So I'm going to cube both sides and then subtract 2. Okay, so there is my inverse. I'm going to use inverse notation here. Here we go. Okay, now to graph this one, I mean, you can do a table of values and try to reason out what to plug in for x, or just take the ordered pairs that are from the blue table and reverse them. Now, make sure they satisfy the equation you just created. So, for example, if I were to plug negative 2 in for x on the inverse. Negative 2 cubed is negative 8. Negative 8 minus 2 is, in fact, negative 10, right? So let's go ahead and plot all those. Okay, and notice we still have that reflection of the two graphs over y equals x. Okay. Example 4. Here, f is the square root of x minus 3. Find its inverse and graph both. All right, so let's start with graphing f. Okay, now the domain here is not all real numbers, given that this is a square root function. Your domain, the radicand, has to be greater than or equal to 0, right? You can't take the square root of a negative. So x has to be greater than or equal to 3. So I'm going to put 3 in as my first value. That's going to produce 0. 4, f of 4 would give me the square root of 1, or 1. I think 7 would be a good choice. 7 minus 3 is 4, the square root of which is 2. Okay, and then I could go up to like, 12? 12 minus 3 is 9, square root of which is 3. So that would take us off the grid a little bit. That's okay. All right, so now we are going to try to find the equation of the inverse. So once again, the original is y equals the square root of x minus 3. We're going to switch x and y. We're going to square both sides. That's going to give me x squared equals y minus 3. X squared plus 3 equals y. Or use inverse notation. Okay, now that's a quadratic, right? What do quadratics graph to look like? They're parabolas, right? So let's do a table of values here. Okay, so I'm going to plug in negative 2, negative 1, 0, 1, and 2. Okay, negative 2 squared would be 4. 4 plus 3 would be 7. Negative 1 squared would be 1. 1 plus 3 would be 4. 0 squared plus 3 is 3. 1 squared plus 3 is 4. 2 squared plus 3 is 7. Okay, so if we plot all of that, negative 2, 7 right there. Negative 1, 4. 0, 3. 1, 4. 2, 7. Okay, we got a parabola like we said we should. Do we have symmetry with f of x? We don't. Okay, now, what that means is we have to eliminate these values where x, the inputs, were negative. And if I do that, that would take off this part of the parabola. Now do we have symmetry? Yes. Okay, so I have a restriction here, okay, that this only is going to work for x values that are greater than 0, greater than or equal to 0. Okay, so let's add that in. only if x is an element of 0 to infinity. Now, why is that? Because the range of the original function f was 0 to infinity. Okay? Questions there? All right, one final one. We've got to kind of hustle here. F equals 4 minus x squared. That's a parabola. I'm going to choose those 5 values to plug in for x. -2, evaluating that at for f is going to give me a 0. F of -1 is going to give me 3. F of 0 is going to give me 4. F of 1 is going to give me 3. F of 2 is going to give me 0 as well. Okay, so that's f of x there. We have y equals 4 minus x squared for the original. To find the inverse, switch x and y. Okay, now probably what I would do is add the y squared over. Make it positive. Then I'd subtract the x over. I would take the square root, and when I square root in an equation, I have to remember about plus or minus, right? Okay, so let's do a table here for this one. Okay, so let's say I plug 4 in. I get 0 out, right? That's okay. Let's say I plug 0 in. 4 minus 0 is 0. 4 minus 0 is 4. Square root of that is going to be 2 or -2, right? So I'm going to have 0, 2, and 0, -2. Okay, 3 would have been another good choice. That's going to give me plus or minus 1. Okay, so what's the issue here with this inverse that I've created? It's not a function. The inverse is not a function. So we say that the inverse does not exist. Okay, and the reason it's not a function is because the original function f had repeat y values. See those 3's and these 0's? Those repeat y's turn into repeat x's when you switch the domain and the range, right? Okay? So this function f is not what we call 1-to-1. 1-to-1. Okay? Click to the last page here. For a function to be 1-to-1, it has to pass both the horizontal and vertical line tests. Okay? The graph on the left here, this cube root function, it is 1-to-1. So it will have an inverse. Okay? This one, not 1-to-1, doesn't pass the horizontal line test, so therefore has no inverse. Okay?